Okay, we're ready to talk about haloalkanes, their nucleophilic substitution reaction, and also their mechanism. The first example I chose was bromomethane, which is a primary haloalkane, and I'm adding it to potassium hydroxide dilute. The products are methanol and potassium bromide. Now, we usually do a kinetic study. If you remember from last year, you change concentration of one reactant, hold the other one constant, and see what happens to a change per unit time. If you compare experiments 2 versus experiment 1, as you change concentration of the haloalkane by twice as much and hydroxide is kept the same, the rate becomes doubled. So this will say the rate of this experiment, and remember these are experimental data, is a constant K times haloalkane to first order. You double the concentration, the rate gets doubled. Now if you compare experiment number 3 versus experiment number 1, you see once halogen is constant and you double the concentration of hydroxide, the rate gets doubled as well. So this also say, look, with respect to hydroxide, the rate is also 2 power 1, or order of reaction is 1. Now SN2 comes to life. The 2 stands for bimolecular. In the rate determining step, both molecules are involved. So this is molecularity, bimolecular, meaning 2 molecules are involved in rate determining step. Now the job of you as a chemist is to come up with mechanism or just recall the mechanism. So what we did is we decided there is only one step in this reaction, in this mechanism. I put my nucleophile, which is the hydroxide, here with its lone pairs. Then I put my haloalkane. I'll give you the tetrahedral sort of a shape of this haloalkane. So what we decided, since there is only one step and I have to show both species in that step, there is a attack. Remember that this carbon is partially positive, bromine is partially negative. So one of the lone pairs of the oxygen with a curly arrow, you should show that, is attacking carbon. And the electron of bromine, the covalent electron of bromine, is traveling away from it. So now I'm going to open a bracket to show this sort of a reaction. There is bromine trying to break away. There is also inversion of the shape. We're not worrying about it that much. And the hydroxide is trying to form a bond with it. Now this is a compound that is highly energetic. The highest activation energy, known as activated complex. And then it will give you the products, which is methanol, and bromine comes out in form of bromide to mix with your potassium, give you potassium bromide. So this is the mechanism for SN2, which applies to primary. So you have to remember it. Primary goes through SN2. There is one step. Since both molecules should be shown in the step, remember to show the activated complex, which has the highest activation energy. If we show the energy diagram for this, if here you have energy and this is your reaction profile or reaction time or coordinate, this is where you have your activated complex. SN2 primary.